Hello everyone, it's September the 5th. Alright, let's go right into it. Orderly queue. You're given a string s and an integer k. You can choose one of the first k letters of s and append it at the end of the string. Return the lexicographically smallest string you could have after applying the mentioned step. Any number of moves. So I can choose one. So I move here, we get ACB. I can move 3, so I have to move BAA. And then we move CAA. Let me see. So this one's what? BAACA. So we move BAA, so it becomes CABAA. And then we move CAB, so it becomes AACAB. Nope, that's not how it looks like. Oh, hold on. We move 3. It's CA. Yeah, it's CA. Choose one of the first. Oh, hold on. Not moving K. You can choose one of the first K letters. So one of them. One of them. Oh, if it's 1, then that's the only one. 3, you can choose any one of 3. So let's say we move B to the bottom, and then we move C to the bottom, become AAABC. I see. We move the B to the end. The second move, we move C to the end. 1000. Okay, so what is our strategy here? Well, lexicographically smallest. So you're moving things to the end, right? And the idea is if we can move something that's big to the end, it's always better. But because it's called orderly queue, so you can only move to the end, right? So if I say if this one is BC, AAA, we shall return this one as well. And actually, you can do any number of moves. So we can move B first, right? Then move C. Right? And just within the first 3. Which means every time you move, you got a new one coming in. Wow, I'm a bit hot. Let me turn down the AC a little bit. I'll be back. Alright, back. AC a little bit down. Alright, so let's go back. I'm saying is every time you move a letter to the back, you actually think about you pushing one more letter to the front, right? So what we can do is we can separate the original string into 2 parts. The first K, right? The first K is going to be a deck. And then the remaining, is actually also a deck, right? So the goal is we move something from the front, we pop left, and then we append on the front by popping left on the back, and then we also append on the back. So it's this kind of, oh, hold on. The front is not a deck. The front is not a deck. The front is, because we can pick any one. So the front is not a deck. The front is whatever it is. The back is a deck. The back is a deck. Huh. No, the front is not a deck. The back is a deck. which means there are, hold on, I'm trying to analyze, see if we can get something out of it. I mean, technically speaking, if we move something from the front, we add another one in, we add another one in, we add another one in, so we push the back forward, right? We push the back forward. So after a couple of times, all the back can be pushed to the front, right? We can just keep going, and then at the end, the back can go to the front. So what we can do is, let's say we can figure out where the smallest letter is, right? And because we can do it any number of times, we can get the smallest to the front, right? So in this case, let's say the smallest is A, right? And we know because A is originally, actually it doesn't really matter where the A is, we can just keep moving the front, right? We keep moving the front, and eventually A will go to the front, right? Now we have a new setup. When we have a new setup, now we need to find out the second position. What is the second position? And we try to get the smallest to the second position and to the third position. Just keep doing this until, because the first K letters, we can just keep moving, right? It doesn't really matter. So anything, we can just shift to left, shift to left, shift to left, shift to left, and we can move any letter, right? Remember, we can move any letter to the front K. Like any letter we want, we can just keep going, just popping, add, popping, add, popping, add, and we can move it there, all right? Therefore, it is possible to get the smallest K letters to the front. It is possible. Now, after we get the smallest K letter to the front, is that going to solve the problem? Like in this case, right? So the first K, we find out we have 3A, right? We find out the smallest is A, and we can just put A in the front, and then B is gonna go to the back. And then the second one is A already, it's fine. And we find the third position, and we have another A, so we can, so we left, if we go first B, will be A, C, A, B, right? And then we say, okay, I want to put A to the front, so we move C to the end, and that is it. What if we're starting with CAABA, right? If it's CAABA, let's say we can get AAA to the front, and we have to move C first, so AACB. Is it possible to keep changing? Maybe it's not possible to keep change. Let me think. If it's CAABA, right? Now we need to go to first position. So we have AA, BAC, right? And our second position is good. Now we want a third position. Third position has to be. So we can move B to the end. But let's say if I don't do that. If I don't do that, can I say like this, CA, right? Now we move B to the end, AACAB. Now it can be AAACB. Oh, it's still AACB. Are you telling me that the relative order among the letters cannot be changed? Let's think it through. The relative order of the letters cannot be changed. Well, it cannot be changed if I move something from front to the back, that's changed. But if I move again, then we change it back, right? So that means no matter how many moves, now what we want to do and what we can do is to stack the smallest to the front. Now after we finishing stacking the smallest to the front with however many moves we have, the remaining is, you're saying the remainings cannot be changed? Like it's not possible to change the remaining order? If that is the case, then this problem is deterministic, right? We can just go straight forward to solve it. Let me think about it again. What am I trying to say? What I'm trying to say is the smallest K letters we can move to the front, right? And that will take, oh God, I actually don't know how many steps it will need to take. It will take however many steps and it requires, and once that's done, whatever the order it is that's left, like no matter how many steps you need to take, we have to push the smallest K letters to the front to make it lexicographically small, right? So that is a must. Now the question is, there are many ways to do that, right? There are infinite number of ways to put the K smallest letters to the front. Now the question is, will these different steps result in different remaining order, right? Different remaining order. It might, right? It might not. Like if the difference between the steps, I think, is like if it's a 2, then it will not. Actually, I'm not sure. Huh. Number of steps needed. If I go here, right, to the front, go to the back, to push this A forward, and this is already A, and so if I go this one again, and push C to the back, and C will still be at the back. What we're saying is we have a relative order of the remaining letters, right? We have the letters that we will keep to the front, and we have the remaining letters. And as we are moving, it's always going to be the remaining letters will get pushed to the back. Oh, the front could be pushed to the back as well, if we need to make room. So they'll get pushed back, and then they'll get pushed back, and they'll get pushed back. So yes, I do think the order of the remaining values will stay the same no matter how many different ways you do to push the first K smallest to the front. And the reason is no matter like the remaining letters will have a starting position, right? We have a starting position, and then we start to change, and all the letters that's currently occupying at the front will have to go to the back, right? And then all the things at the back will be pushing forward. And then, yeah, I don't think there is a way that they will result in different. You might have different order. Like you say, okay, I don't want to push it now. Like if you don't push, because there are only 2 situations for you to pop, right? So one situation is you have some letter that's not supposed to be in this position, and you pop it, right? And You can choose not to pop it, but eventually you will have to pop it. And regardless, eventually you have to pop it. So that those will be popped to the back. You can choose not to pop, but eventually you will pop. And then I just say, like, if I pop, right, and then the rest happens, and I got moved to a certain position for the remaining. If I don't pop, then everything else is not going to be in place. Then I pop, right? Then I pop. Then I'll be ending up at the end. I might think this is, hold on. Let's go back to this. So BAACA, right? What if I don't pop the first B? What if I pop the A, the second A, right? And now I pop C. And then I pop B. I can reach AAACB. Yes, so it is possible to reach a different configuration. So it's not just the first three. You also have to think about how the remaining can work. Interesting. Very interesting. What's the verdict? I don't know. We have first K and then the remaining values, right? And then who to pop? The one that's not supposed to be at that position, right? So we can gather the top smallest. So we have, let's say, a dictionary of A, B, C, D, right? And we have their count. We have their count. And after the count, we know which position it should be, right? So we say, in this case, A shall be in position 0, 1, 2. Now we look at it currently. Currently 0, 1, 2. 1, 2 is occupied, but 0 is not occupied. But we can choose to pop 0 or not pop 0. That's two orientations. If I pop 0, what happened is they will move forward, right? And then this one will be pushed to the front, and B gonna be add to the end. And now we have to check again. Oof. That is not how I imagined it to be. I mean, we can definitely sort it, right? Because in this case, we can sort it. If we sort, it's going to be ABC. But then I need to prove that we can do ABC. Let me think again. So if a value, like it's a B, it's occupying the position it's not supposed to occupy, then B will get popped no matter what. It's just a matter of time. But when should we pop it? It's a good question. When should we pop it? Can we analyze, like, we have the top K, right? We have top K, and then we run a comparison. But the thing is, every time you pop, then the string changes, except for the one that's already settled. Then we know the later you pop, the more to the back you are. Can we do like analysis? Say we have the front K letters, and then they have a certain position is good, certain position is not good. And those not good position needs to be popped. Then we need to make a strategic decision which one to pop first. Well, we definitely, right, because the earlier pop, it will keep pushing forward, right, push to the front. So what if we say we always pop the smallest of the value that is not supposed to be in its position at the moment? We pop the smallest. The smallest go to the back, right? And then something else come in. And we have a new match, right? A new match. And we pop the smallest. But then if we go to the front, right? We go to the front, and if we pop it, then everything shifts. That changed things, right? That changed things. It's not position. It's the current value. If we pop the small one first, and then pop the large one last, I need another example, man. What if this BACA with a K equals 2? Right, now we find we have 3A, 1B, and 1C. And then we say K equals 2, so we should make both A's at the front. Right, that's our goal, to make both A's at the front. So in order to make both A's at the front, then we check. We check the current. We check the current orientation, and then we find out that there's a B in the position that's not supposed to be. So we move B to the end. So we pop B, because we have to pop B anyway. But with that, we have a problem. We pop B, B go to the end. Now it become AAC. Wait, hold on. B popping AACAB, right? So it become AACAB. Now the front is done, but I'm pretty sure we shall keep going. Like, can we keep going? Yeah, we can keep going. We can pop A, then pop C. Now we become AABAC. First, we have AACAB. So AABAC is smaller. Right? We'll actually keep popping. We actually cannot keep popping. So it's AABAC. Right, so it's AABAC. I think. Hold on. BAACA. Let's say we have 2. Is that AACAB? No, AABAC. No, oh wow. You can go back to AABC. Wait, hold on. How? BAACA. And so we do this. Then we do this. Then we do this. Right? Then we do this. Oh, wow. Yes, AABC. Huh. Hold up. Hold up. What are we saying? If we have k positions, we can align the smallest k to the front. We can also align the remaining values in an increasing order as well to the front. Yes, we can align any value to the front. And once those are at the front, then what? Then we pop, and they go to the back. And then what? And then we're trying to adjust. And every time they come in, we go pop. But what's the strategy again? The strategy is depending on k, right? Because what we know is if the remaining values are set in order, the remaining values set in order, which we can do, which we can definitely do. Okay, let's say if the remaining values are set in order and we don't care about the others, then we do a push. Get the remaining values to the back. And it depends if the remaining values, number of remaining values is equal, smaller or equal to the k, then we can do that. We'll get the remaining value to the front in sorted order, and then we can push them all to the back. All right? And then, let's say those values are not of our concern anymore, because whenever those values get to the front, we let them get to the front and we push everything back. Then what? I have a bunch of values with the remaining values from small to large. And then we also have the k values that we know we can go put in the front, right? K values that we can put into the front. Then we can try just to do that, to get the k values to the front. And as we're getting the k values to the front, the remaining values, the first k remaining values will always be in place. Or it depends. It depends on how big k is. Alright? Alright, let's put it this way. If k equals the length of the string, then we'll just return the sorted order. Alright? And now k will get smaller, k will get smaller. But if the k value, right, is larger than the remaining value, the number of spots for the remaining value, then we can easily sort the remaining values in the first k. Yeah, we put the remaining values in there, and we can load them to the back. Now in the front k will be front k, we can just organize those, like putting whatever, the smallest, right, to the front, smallest to the front, smallest to the front. And as we are putting the smallest to the front, something will go to the back, something will go to the back, blah, 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 blah. Doesn't really matter, doesn't really matter. And then they will enter, and then to the back, right, to the back. And then when the remaining enters the first front k, right, and we don't have any more to move, what we're going to do is simply move them to the back. Right, so they will always be sorted, and they will always be moving to the back. And then we keep adjusting, and eventually we have the front k will be the smallest, and the remaining will be the largest, basically, largest. Which means if k is larger than half the size of the original, right? If k is larger than half the size of the original, then it's always possible to fit the remaining. We can get the largest, right? The largest sorted way, the remaining, into the front, right? And then I push them to the back. And the remaining is all sorted, right? From the largest part is all sorted, and the front part will be the smallest that's supposed to be there. And then we can always do this move. We can sort the front as well. And as we sort the front, the remaining one gets pushed front, right? And but it doesn't matter. We push to the front, and we simply just keep pushing them to the front. And then let's say we keep them pushing to the front, and then we push them back again, right? And then we push this, right? So however we want, we push this, get them into position. We push this, get into position, and we get push. So yeah, that is my conclusion. If k is larger than half the size of the original string, we can always return the sorted string. Yes, so k is 3, larger than half, we good. If k equal to half, I think it's also good. Now, what if k is smaller than half? If k is smaller than half, then the remaining cannot fit in the front, right? We can only fit the biggest to the front. And so in that case, what we're saying is we can get the smallest to the front, get the biggest to the back, but there will be certain number of strings that we cannot sort. Do they stay as its original order, or can we also flip them? Let me think. The front is small, right? And the same way, we get the largest largest k to the front, The other one doesn't really matter. They just keep going, keep going, keep going, and then the largest go to the front. Now, once we do that, no matter what, yeah, they do change positions though. They do change positions. Huh. Yeah. And then what? And then we push them to the back. Now we have something at the front. We all can also sort them based on the small values, which take them, we go here, we go here, we go here. All right, and then we keep going, keep going, keep going. We'll always end up at the front. So what we're talking about, we move those to the back, right? And then we try to figure out how to move the other one to the front. And then we can just keep moving, keep moving, keep moving, boom, to the front, right? And then we move this, they're gonna move back. Keep moving, keep moving, keep moving, keep moving. So get the front. And then if they're not at the back, we just keep moving, keep moving, keep moving, keep moving. Move them to the back. Well, can they even be moved to the back? So if I move this to the back, yeah, what if it happened like the front is set and the back is set, but it's not really at the back position? Then what do we do? Can we just go, and then we just keep moving. Right, we keep moving until we get it to the front, and we move and move. Oh, that's actually complicated. I actually don't know. Hold on, let's do this one more time. What we can guarantee is if we're given a string of length n, and our k is larger than half, larger or equal to half of n, then it's guaranteed. It's guaranteed that we can return a sorted array, a sorted string. Now, in that case, right, so in this case, 3, 4, and 5, we actually do, like, doesn't matter how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like 30 something. If I just do 20, right, it will always be sorted. This one will be always sorted. Yeah, it will always be sorted, and I can't even decrease it. I think 18 will always also be sorted. Actually, let me see how long this one is. Let's say PT Python. All right, 36. So we can do 18. I think 18 will still work. Fully sorted. 18 will still fully sorted. And then from 18 to the will be fully sorted. Now, if it's not, that is the thing, right? If it's smaller, which means only a small portion can be sorted, right? If only a small portion can move, then what? I mean, then what we're saying is we can sort, let's say 1, 2, 3, 4, 5, right? Now we can sort 6, 7, 8, 9, 10. We can sort these. But that's not the case, right? We can get the small values, right? We can get, say, 1, 2, 3, 4, 5. We can get these at the front. But once we get these to the front, other things will change, will move, will constantly be moving. How do we fix that? All right, this is just way too complicated. Let's get this. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So if I go 5, as my theory goes, this will fully sort. Yeah. But now let's just say if we do 3, right? What's going to happen for 3? If we do 3, we can get F in. But there are many ways we can get F in. All right, so if we do 3, we know we can sort this much. That is what we can sort, right? Not really, because these are included. So it's actually not. We cannot sort this because the sort requires everything, so these will constantly moving. Huh. If we want to have 3, we can move F in, right, by S and H. Let me just take a look. Maybe I get some intuition. Is it just to get... No, it's not just to get S and H. You see the ABF. Actually, it's everything. We sorted everything. Whew. Hold on. Let's try this. Might not be a good test case though. It's too long. A, B, A, C, F, J, G, K, J, right? So, what are we saying? We're saying that if we move the largest to the front, so it's JKS. So let's move J to the front. So J, G, K, J. And everything at the front just move back. A, B, S, H, F, right? And then we want to move K. Okay, so we want to move K. So J is done. We want to move K, so we only need to do this. And then we want to move S, right? So basically we're going to say JAB. So we now have JKS, HFG, JAB. And then we move JKS to the back. Now we have HFJ and G, JAB, JKS. So JKS is in position, right? So they are in position. Now we have the front, right? Now we have the front. Now when we have the front, let's say we want to move AB to the front, right? Let's just let's move AB to the front. So when you say it's going to be AB, JKS, and then everybody just go to the back, HFG, J, right? Once we've done that, we say, now what do we say? We have AB at the front, but JKS is not. So it's not how it's done. We need to make AB to the front while maintaining JKS at the back. Well, how can we do that? They'll always be together. No, not really. If we go AB, Now we go A and we go B, and then we go. No. They are always together. So that's not the way to go. We need to create space, right? We need to create space between the front and between the back, which means I say if I have A, B, A, H, F, J, right? That's 6, length of 6, with 3 I can move. Then I can always move to however I want. But now we have something attached to the back. If we have something attached to the back, then the way it moves is different. So it won't fit, right? That's the problem. It just doesn't fit. How do we figure this? Yeah, JK is the front, AB at the back, but that doesn't work. So we want AB at the front, right? We want AB to be at the front. Hold on. What are we saying? Let's keep the largest value at the front, right? And then we can do the maximum separation, right? And then we go the second one. No. Oh. Okay, what were we saying? So let's say we can move. So S is the largest, right? So let's say we move this, right? And then we move here, right? So now S and A is in this position. That's a good position. Then we go. Right, now we got the front and back done. Then what? Then I say we can look at the second one, right? So I want the second largest, which is K. So I want to move K there. So what do? We do KJS, right? So move K there, so KJS, BHFJG, right? Once we do that, K is in place. So now what we want is to put B at the third position. Right, so we can say AK BHFJJ we go JS, right? So we move that, S go to the last position again. And then we can move K. Oh, shoot, not be SK. So B and K. So what we want is the smallest and the third largest. Like this. And then we do this, and this, and then this will, yeah, we do this and this. This gets pushed back, right? And now to the third one. Third one we can move here. All right, so we push these two in position, and we're going to push the third one. So the third one. What I'm saying is, once one position is done, and a problem is simplified to doing this, right? We try to order this with 2 to go. Now once B is done, it will be this with 1 to go. But the thing is, it changes, right? There's so many ways to get A to this position. And how about, what if, say, we try to get F to this position, right? We try to get F to this position. Still no clue, man. No clue. What if I only have 2? Just playing around. And I want to get it a little smaller as well. I don't know. I try to just see if there's anything. Wow. We got everything. Alright, if it's 1 around, only 1, k equals 1, there's no way we can do. Yeah. If only 1, then it is what it is. If A is already at the front, and that's it. There's nothing we can do. Right? But if we have 2, then we can have all the difference that we can make. What is the trick? This, you know what? This has a Tower of Hanoi feeling to me. Recursion. Don't think too hard. We can move one of the first 2, and then we have to push to the back, right? So we can do one of the k moves. And so once we move, but there's no end state. Yeah, the front is already set, right? I have no clue. Ah, this one got me. I have 5 more minutes. If I still can't, then I need to search for some clues. Not necessarily solutions, but just clues. I don't know. I mean, I have solved part of it, right? I've solved part of it. It's just when k is small. What is the trick when k is small? K is small. What are we looking at? I don't know. I mean, let's just say we want. Okay, this part. So what? We need to go HS, right? So we go H and go to the front. So we say H, J, right? And then boom, 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 ABS. And then we need S. So H, S, right? And then ABFJ, right? And then boom, go ABFJ, go H and S. That's like sorting the first four, right? Well, it's not really sorting the. We can sort the first four. We can. Yeah, I think we can sort the first four. It's just we have something in between, right? So we don't care whatever is in between. We can sort the first four. And once we're done, we sort these four. And once we sort these four, we can do that. So that's going to be FJ, HS, AB, right? And then we can go to these are already sorted. A, B, and J. Sorted. Then what? Then we say this. See if this one's sorted. We can sort this. We can sort these four. So these four will be sorted. How do we sort it? So it's going to be. So we're going to be JS at the end, right? So what we want is J, H, S, A, B, F, and then this, and then A, B, F, H, J, S. Hold on. What is this? What is this? Okay, what I'm trying to say is we can always sort. Like if the k is smaller than half, that's fine. So we can always sort the first 2k, right? We can sort the first 2k letters. And when we sort them, it'll be the first 2k, something, something, and gigantic bunch in the middle, and then something, something at the back. So these are sorted, right? They're in sorted order. Now we can sort once we sort these, hold on. What are we sorting? We sort this, which will end up in small, small, and the large, large at the back. And then we sort this, right? So what we're gonna get is sorted sorted, right? Something in the middle. And then this we can go again, sorted, sorted, and sorted. And again, sorted, sorted. So every K will be sorted. And then how do you make these can be sorted, right? Yes, we can sort them. We can get biggest, and then we can get the biggest to the back. I shouldn't say sorted, we just can get the biggest to the back. For the first two, right? So we can get the biggest to the back, and then for the remaining, the next biggest to the back. Oh, it's actually not the biggest. We can put any two values up front, right? Let's say we have a k and the remaining, right? So k, so we can put k, depending on how many times we need to do, right? So we can put this, boom, to the back. And then when we do that, can we just ignore the back? Only focus on the front values. We focus on the front values. Say, what do we need for now to put in the back? Okay, let's say we need to put the next to the back. And then they will go, they will go, they will go, like however they go. And those two will always go together. The one sorted will always go together. Right? And then the other two will boom, boom, they will go to the back. But it's not guaranteed that there will be no gap in between. There might be gaps. All right, I need a hint. I need a hint. Oh, I think the streak ends today. I need a hint. Related topic. Math. Ooh. Math. I don't know. Take a look. It's just mathematical. If k is 1, if k larger than 1, any permutation of s is possible. Huh. I was able to prove k is larger than half, but now they're telling me k larger than 1. All right, let's give up. Let's just try to understand. Case a k kick. Oh, one kick move. Yeah, a one kick move is just a rotation. So we just keep rotate until the smallest value go to the front. Two kick moves. It allows to swap the position of two adjacent beads. Every permutation of necklace is possible. Hold on. That is a good intuition. So we are doing a necklace thing. It's just each bead is a tuple, is a two-element tuple. So we can move those, right? We can move those around. But then what? I mean, what we can, like what I, okay, let me think. What we can do is we can get the beads, the smallest two together, all right? And then those can move to the back. And then we can get the next two smallest together. And to do that, we can always make sure that the previous one always stay together. Okay? The next two smallest together. And the next two smallest together. Whatever. So like you can always do that. But my question is, as we're doing this, there will be gaps. Like how do we guarantee that there'll be no gaps between the consecutive beads? As if there are gaps in the beads that we cannot decrease the gap. Or can we? Hold on. So what I'm thinking is with two positions, right? K equals 2, we can get consecutive two letters, consider them as beads. We can create them, right? But the problem is once we create all these beads, these sorted beads, what we do not have, we cannot guarantee is there might be disorder. They will not be ordered, right? There will be gaps in between or whatnot. Then what? Like if we have gaps, right? So like the smallest and they like right next to each other. Then what? Yeah, then what? Then okay, read again. Every okay, to actually convert, we bring the second smallest bead to be after the smallest, and the third smallest to be after the second smallest. Like how? If we perform a two-kick move followed by many one-kick moves, we can transform a string like this to this, proving that we can swap the positions of any two adjacent letters. Hmm? I know this. How do we bring the third smallest to be after the second smallest? Okay, this one says we can swap Yeah, I mean, for sure, we just move y to the front and then move x. Yeah, I know that. But what if I want to swap x and z? Okay, we can swap x and z. Hold on, hold on. If I want to swap anything, right? If I want to swap anything, all I need to do is bring them to the front and we can swap them, right? That's possible. Just bring them to the front, we can swap them. So this proves that adjacent any adjacent letters can be sorted, right? Any adjacent letters can be sorted. Okay. Then what? We sort the smallest, okay. And then push this to the back, and then we push the next one in. We sort the next one. Push them back. Hold on. We sort two at a time, right? So we sort two, and after that, we push one to the back, all right? And then next one comes in, and we can sort the next two. So we'll just go get the next one, right? We're good, and push this one to the back. Then sort the next one, right? And then these will just keep going. They will keep going, and then we sort, keep going back, and then I think I got it. I think I got it. No, I don't like this explanation at all. But here's what I think, right? So we can sort the smallest. We move the smallest two to the front. We sort the smallest two, right? After we sort, we put the smallest to the back. Doesn't matter. Now we have the second smallest at the front, and we just find the third, right? We find the third smallest, and then we put the third smallest at the front at this position, and put the second smallest at the back. Now, when we do that, we will have gap, right? We'll have a gap between the smallest and the second smallest. But don't worry about the gap. So next one, we're looking for the fourth smallest, right? So as we go, we always only change in this position, right? We only change in this position, right? We only change in this position. We don't have to change this. So we just go the single beat thing, right? Single beat thing until we find the one we need, and we push this one down. And then we just keep going. So every time, every rotation of the beads, of one kick, every rotation of the beads will get one value into position, right? And then keep going, and next value into position. If the one's already in position, when we encounter it, we just push it to the back, push it to the back. So as we keep going, the not in position one will be captured, right? Throw it to the will be captured, and then which means the remaining. So we'll have something at the front, and the remaining ones, as we go rotation after rotation, we will constantly push in the sorted order into it and take in the not sorted out. Push sorted in, take the not sorted out. Therefore, with a 2 kick, we can always. This makes sense now. Okay, don't have to do anything. Why O square? I don't have to be O square. O to build the string. Now we just Oh, it is O(n) squared because it's rotating, right? It's rotating. If we have multiple smallest, so we have to check every single one of them, right? We check the first one, check the second one, check the third. We have to check every single one. That's why it's O(n) squared. And that's O(n) log n, so overall O(n) squared. Ha! Oh, is O(n)? Oh, nope, nope. Very interesting. Uh-huh. Rotate the whole string except the first letter, right? Rotate the letter to the start, and rotate ith letter to the second position. We can bubble sort the whole string. Ah, oh, this is bubble sort. I plus 1's biggest letter to the start, and then rotate ith the second. And then boom. Yeah. Yep. All right. So, okay. All right. We didn't figure. I would say we figured out that when k is larger than half, right? That's what we were able to figure out. But what we did not figure out is it works when k equals 2. All right. Oh, I just code it up and then call it a day. Wow, our streak ends today. Okay, so this is LeetCode 899. I didn't solve it. I had to check the solution. I was halfway there. But fell short. I was able to figure out that when k is larger than n divided by 2, larger equal to n divided by 2, we simply solve the string. But the real solution is that when k is larger or equal to 2, we can sort the string. The reason is we can always move the ith and I plus 1th smallest value, right? Smallest values to the using k equals 2 as an example. K larger than 2 can be solved by k equals 2 condition. Right? We can always move the smallest and this value to the front, right? To the front 2 positions. we then move the ith smallest to the end. Then next we look for the I plus 2 smallest value to the second position. Once that is done, we move the I plus 1 smallest to the end. Right? We keep doing this. We keep doing this. The string, right? The string goes in round and round, and each round, one more sorted value is added to the remaining string, and one more unsorted is picked out from the remaining string. Sorted value is added to the remaining n-1 string, and one is picked out from the remaining n-1 string. When the last unsorted value is picked out, we have sorted the string. Therefore, when k is larger than or equal to 2, we simply sort the string. Reference here. It is, right? It does feel like bubble sort. Ah, yeah. We can always switch. The array is arranged. This is basically bubble sort, yes. With the ability, thinking from another perspective, with the ability to swap the first two elements, what we have is the same platform as bubble sort. Right? Swap, and then we can bubble. Right? We can bubble the biggest value to the end, and then the next one we look for the next one. So like each round we find the largest value and bubble it to the end. Yeah, that's basically what it is. Actually, it's not the biggest value. It's the and it doesn't matter, biggest, smallest, it's the same thing. We bubble it to the end. And then we find the next one, we bubble it to the end. Next one, so as we keep going, yeah, you know what? I just mentioned it's the same as bubble sort, but I'm not going to do it. So I think this is a better way for me to analyze. All right, so if k is equal to 1, what do we do? So we're going to say s list equals list s, right? So if k is equal to 1, so we have to go through every single construct. Oh, maybe I can just use, you know what? I think it will be better if we use like res equals, res equals s, right? And then we just say for I in range len s. Right? I range len s. Res equals min. Res, and then gonna be s to I, right? And then plus s. And you know what? No, it's gonna be s plus s I to the n plus I to I, right? That's just swap, and then we can go actually from 1 to len s, right? Else s equals to, you know what? I actually don't like this. Let's just do it this way. And then return res. Else we simply return sorted s, then this dot join. Okay. So let's run test case. Just in case my dumbass will get something wrong. Alright, so we have CBA 1. That shall give us ACB. Right, and then next one is doesn't matter, BAACA 3, give AACB, BC. We have S and K. This is going to be order S and K. Yep. That's fine. I mean, we've been on a streak. We've been on a good streak. Oh, hold on. Don't submit here. Submit here. They don't accept it. I have to submit here. Yep. ON squared. All right, ON squared. ON squared because ON squared for k equals 1 and O n log n for k larger equal to 2. Thus, overall, it's ON squared. All right, that'll be it. I mean, we didn't do this one, but it doesn't make sense, right? It doesn't make sense. We're kind of close, but should have kept thinking hard about this rotating thing. Anyway, that'll be it. That'll be it for today. I'll see you guys tomorrow. Adios.